In this lecture, we're going to cover section 2.2, which is more on functions and their graphs. So we're going to continue the lecture that we covered in the last video from 2.1, and now we're going to look at where a graph might be increasing, decreasing, or staying constant. So we're going to kind of continue on with graphs, and now we're going to look at this perspective. So we're able to look at a graph and say where the function's increasing, decreasing, or possibly staying constant. So a function is going to be increasing on an open interval I if, and I think the easiest way to look at this is if we look at the graph on the bottom left, if we read the graph from left to right over the interval I, as x is increasing, y is increasing also. Alternatively, a function's going to be decreasing. We look at the second graph on the bottom. If we look over the interval I, right? So as we go from, let's say, x1 to x2, so as the x values are increasing, the y values are decreasing. The graph is going to fall from left to right. And it is also possible that a function is constant over some interval I. And what that means is if we look over the interval I, like suppose we go from x1 to x2, if we follow the graph, the y values are staying exactly the same, right? The y value at x1 and the y value at x2 are equal. So this function would be an example of a function that's constant. So let's just practice. Let's look at the first example. So example 1, let's state where the function is increasing, decreasing, or staying constant. So let's look at the first graph on the left. So we see, as we look at the graph from left to right, that the graph is decreasing over an interval, then it starts increasing over another interval. So what we want to do is identify the two intervals for x where the function is decreasing, meaning where the graph is falling from left to right and the y values are getting smaller, and then where the graph is increasing. So where the values of the function are increasing over the interval. So let's identify those. So let's highlight the portion of the graph that's decreasing in red. So let's write this decreasing interval first. So the function is decreasing, and notice coming in from the left, really this graph is continuous, right? So the higher we go up here, the more left the graph is going in the x direction, right? So from negative infinity, so we're looking horizontally, right? So from the left, the graph is decreasing from negative infinity all the way to x equals -1, right? And then let's highlight in green where the graph is increasing. So the graph is increasing over this interval. Now let's identify the interval. So it's increasing over what x values. So it's increasing from x equals -1 all the way to infinity, right? Because this increases forever and it's going to horizontally span, right, all of our x values towards infinity. So that's where that graph is decreasing and increasing, and there's nowhere on that graph that the graph is staying constant. So let's look at the next graph. So on the next graph, we see that there is a constant portion of the graph that I just highlighted in green. So let's do that first. So the graph is constant for what x values? So everything from negative infinity up to 0, right? That's where the function is constant. And then the function is increasing over this interval, right, over this portion of the graph that I'm highlighting in red. So the graph is increasing from x equals 0 to infinity. So over the rest of the life of that graph, x is approaching positive infinity. So the graph is increasing from 0 to infinity. And then let's look at that last graph. So why don't we, in green, let's highlight the portions where the graph is constant. So I have a piece of the graph here and then here in green. So there's two portions of the graph where the y values are staying constant. Now, what interval for x is that, right? So this piece on the left, the graph is constant from negative infinity up to x is -2, right? And it's constant again from 4, right? X equals 4 to infinity. And then let's highlight in red where the graph is increasing. So the graph is increasing from x equals -2 to 2, right? But then it's still increasing after that, right? So we could just make this one interval. So it's increasing from -2 to 4. And then at 4 to infinity, it stays constant, right? So that's how we determine the intervals on which the function's increasing, decreasing, or staying constant. Next, let's look at symmetry. So a graph might have symmetry. And there's three types of symmetry that we're going to look at. So the graph of an equation is symmetric with respect to the y-axis if for every point xy on the graph, the point -xy is also on the graph. So let me give you an example. And actually, I could do it right here. I have room. So suppose here's x, here's y. Imagine my graph looked like this. This graph has symmetry with respect to the y-axis because if I folded the graph in half vertically over the y-axis, the two pieces of the graph would match up. They're mirror images of one another. And what that means in terms of points on the graph, like let's say, for example, this point is 2, 3. If I were to fold the graph over so that it matches up with the picture of the graph on the other side, that point 2, 3 would match up with this green point, right? And that green point, notice it has the same y value, it's 3, but since it's on the opposite side of the graph now, the x value becomes negated. So this is going to be the point -2, 3, right? So that's why if for every point xy on the graph, there's going to be a point -xy also on the graph, right? The negated version of x because we're flipping it over the y-axis. So if we were to substitute -x in for x in the equation of the function, it's going to result in an equivalent equation. The graph of an equation will be symmetric with respect to the x-axis if for every point xy on the graph, the point x -y is also on the graph. So what we mean by that is, I'll do another example over here. So let's say we had something like this. Here's x, here's y. And let's say we had something like this. So now if I had the point, let's say 2, 3 on this graph, and we were to fold the paper in half horizontally along the x-axis, these two pieces of the graph would match up, right? And now this green point that this red point would match up with if we were to fold the paper horizontally, the x value is going to be the same, right? It's still going to be 2, but now the y value becomes -3, right? Because we're taking that point and we're reflecting it over the x-axis, so we're negating the y value. So if we were to substitute -y for y in the equation and it results in an equivalent equation, then we say that the graph is symmetric with respect to the x-axis. And then the third case is the graph of an equation is symmetric with respect to the origin if for every point xy on the graph, the point -x, -y is also on the graph. So if we were to substitute -x for x and -y for y in the equation and it results in an equivalent equation, then the graph has symmetry with respect to the origin. So let me give you an example. So suppose for this case, let me do red. Here's x, here's y. If I had something like this, and let's say this is the point 1, 1. If we were to reflect this point 1, 1 over the y-axis and then over the x-axis, we're going to land here on the graph, right? And what we did was we went over the y-axis, so the y value got negated, and then we went over the x-axis, so now the x value is negated, and now we have the point -1, -1. So we say that this graph would have symmetry with respect to the origin. So let's test for symmetry in the next example. So in part A, we have y equals x squared minus 1. So we want to determine whether the graph is symmetric with respect to the y-axis, the x-axis, or the origin. So rather than going through all three tests algebraically, like we did up here to see, okay, is the graph symmetric with respect to the y-axis or the x-axis or the origin? Let's graph it, see what it looks like, and then if it seems to have a certain type of symmetry, let's test. So let's graph y equals x squared minus 1. So y equals x squared minus 1. And I'm not sure what my window is set to, so I'm just going to do zoom 6, which is zoom standard, my 10 by 10 window. And I see we have a parabola and its vertex is on the y-axis, right? So it looks symmetric with respect to the y-axis, right? If we were to fold, imagine this graph was on a piece of paper and we were to fold it vertically over the y-axis, there'd be a mirror image, right? So why don't we test for symmetry with respect to the y-axis? So remember, if a graph has symmetry with respect to the y-axis, if we substitute -x in for x in the equation and it results in an equivalent equation to the original, then there's symmetry with respect to the y-axis. So let's substitute -x for x. So we would have y equals, we're replacing x with -x, so we would have -x squared. And then minus 1. And -x squared is -x times -x, which is a positive x squared. And look, it's the same as the original equation, right? Y equals x squared minus 1. So since they're equivalent, we would say that this has symmetry, this graph has symmetry with respect to the y-axis, just like we suspected. Let's look at the second graph in B. So we have y equals the square root of x. Let's graph it. So now we have to clear that out. We have y equals, let's pull up the square root, and then of x, and we'll graph it. So this graph only lives in the first quadrant. So if I were to fold this piece of paper over the y-axis, it wouldn't match up with anything, right? Because there's nothing in the second quadrant. The same thing if this were a piece of paper and I folded it horizontally across the x-axis, there's nothing there. So the graph would match up with nothing there. The same thing with the origin. Imagine folding this paper or taking that graph and flipping it over the y-axis and then the x-axis. It doesn't match up with anything. So this graph looks like it doesn't have any symmetry with respect to the x-axis, y-axis, or the origin. And let's check that algebraically just to confirm. So if the graph had symmetry with respect to the y-axis, then if we found f of negative x, it would be the same as the original equation, right? But f of negative x is y is equal to the square root of negative x, right? And that's not the same as y equals square root of x, right? They're not the same. If there was symmetry with respect to the x-axis, then if we substitute in y, negative y for y in the equation, and we got the same equation, an equivalent equation, then there would be symmetry with respect to the x-axis. So let's see what happens when we substitute negative y for y, right? So really what we're doing is we're negating f of x, because f of x is just equal to y, right? So this would be negative y. We're negating the y value now. And that equals the square root of x, which is not the same thing as the original, right? And if there was symmetry with respect to the origin, then we would have to find negative f of x. So we would have to negate y, and we would have to negate x. So if we did that, if we negated both x and y, we would have negative y is equal to the square root of negative x, right? And that's not the same as the equation y equals square root of x. So this does not have any symmetry with respect to the y-axis, x-axis, or the origin. And then let's look at the last one. So let's look at C. So x equals y squared plus 6. Now, to graph this is a little bit tricky. So I'm just going to graph this, but I'll tell you how I'm getting this graph. So remember, when we go to the calculator, we always have to write it as y equals, right? So if I solve for y right now, I'm going to get x minus 6 equals y squared. And then I would have to take the square root of both sides, right, to get y. But since I'm using my square root property, I have two roots. So it's going to be plus or minus the square root of x minus 6. So let's graph that. So we have plus the square root of x minus 6. And we also have minus, right, the negative root. So the negative version of the square root of x minus 6. So let's graph them both. And you'll see we end up with this parabola that looks like it was flipped on its side, right? And we can make the window a little bit bigger. Let's go in the x direction to 20 because it only goes to 10. This way we could see a little bit more of the graph, right? So it looks like it has symmetry with respect to the x-axis, right? Because if we fold this in half along the x-axis, the two pieces of the graph are going to match up, right? So let's test for symmetry with respect to the x-axis. And to do that, we have to negate the y value. right? So let me go back up here. So in order to test to see if there's symmetry with respect to the x-axis, we have to substitute negative y for y. So we're really negating the y value, right? So we're negating f of x. So if we go to the equation, x is equal to, instead of y, we're going to replace it with negative y and then squared plus 6. And when we simplify, we get x equals negative y squared is negative y times negative y, which is positive y squared plus 6, which is the same as the original equation, right? So since they're the same and we just checked for symmetry with respect to the x-axis, it has symmetry with respect to the x-axis. So that's the difference between symmetry with respect to the y-axis, the x-axis, or the origin. Now, the last part of this section is piecewise functions. And you might remember piecewise functions. A function that's defined by two or more equations over a specified domain is called a piecewise function. So in example 3, this is an example of a piecewise function because you see f of x is not just equal to one equation. It's equal or defined by two equations in this case over two specific domains. So like, let's just look at example 3, for example. F of x is equal to 3x plus 5 only if x is less than 0. Otherwise, f of x is equal to 4x plus 7 if x is greater than or equal to 0. So this function is defined by two different equations, but it depends on what your x values are, right? So for example, look at A. It says find or evaluate f of negative 2. Well, x is negative 2, right? Negative 2 is the x value. We want to input it into the function. But what part of the function is x equals negative 2 defined, right? Which domain does negative 2 belong in, right? Is it a part of? So you see how we only use 3x plus 5 if x is less than 0. And in this case, negative 2 is less than 0. So we have to use this top function. So f of negative 2 is equal to 3 times, I'm going to input negative 2 and then plus 5. And we're going to get negative 6 plus 5, which is negative 1. So f of negative 2 is equal to negative 1. Let's look at B, f of 0. So we have to see what function we're going to use. Not function, but which equation, right? The 3x plus 5 or the 4x plus 7? Well, it depends on x. X is 0 in this case, which is going to be part of this domain that I just circled. X greater than or equal to 0, right? X is allowed to be greater than or equal to 0, like in this case. So I'm going to use the equation 4x plus 7. So we're going to have 4 times 0 plus 7, which is going to be equal to 7. And then let's do one more, C. So f of 3. 3 is part of this domain, right? X greater than or equal to 0. 3 is greater than or equal to 0. It's greater than 0. So I'm going to use 4x plus 7 again. So I'm going to have 4 times 3 plus 7. That's going to be 19. 12 plus 7. So that's how we evaluate a piecewise function at a given value. You just have to look at which restriction or part of the domain, right, that X value satisfies. So let's practice graphing a piecewise function. So let's look at example 4a. So f of x is equal to 3 if x is less than or equal to -1. Otherwise, f of x is equal to x minus 2 if x is greater than -1. So let's just graph one piece at a time. Let's look at the first piece, f of x equals 3. F of x equals 3, or remember, f of x is the same thing as y. So this is the same thing as y equals 3. That's just a constant, right? It's a linear function, and it goes through y equals 3. But look, we can't draw this piece of the function like this because we're totally ignoring the domain, right? The restriction on this part of the function. Y is only equal to 3 if x is less than or equal to -1. And here is x equals -1, right? I just circled x equals -1, which is right here where I'm putting the point. So y is only equal to 3 for all values of x that are less than or equal to -1. So we got to get rid of the rest of that line, right? It doesn't belong because this is only defined for values of x that are less than or equal to -1. So that's that piece of the function. Now we want to graph f of x, or y equals x minus 2. But it's only for values of x that are greater than -1. So we can make a table of values. Look, if I make a table of values, pick values of x, right, that are greater than -1, as long as it satisfies the domain. So a value that's greater than -1 is 0. Plug 0 in to this equation for x. 0 minus 2 is -2. So there's one point we could use, 0, -2. Pick another value that's greater than -1. What about 1? Plug in 1. For x, 1 minus 2 is -1. So I have the point 1, -1. Let's pick one more number. How about 2? 2 is greater than -1. If I plug in 2 into my equation, 2 minus 2 is 0. So I get y equals 0. Now I want you to see, so in green, I'm gonna choose, I know x has to be strictly greater than -1, but let's use -1 because I want you to see something. And I'm doing it in a different color for a reason. So look, -1, if I plug in here, -1 minus 2 is -3. So I would get the point -1, -3. But x has to be strictly greater than -1. So this is actually going to be an open circle, right? Because x could be anything greater than -1, just not -1 itself. So look, I'm going to put an open circle on the point -1, -3. So go back 1, down 3. I'm going to put an open circle. And then now for the other points, since they are part of this equation, we're going to do 0, -2. I have 1, -1, and I have 2, 0. So now I'm going to connect these points, right? So this would be my other piece. This would represent the line y equals x minus 2, but only for the values of x that are strictly greater than -1. So it's very important that we keep an open circle on that point -1, -3. So that would be my piecewise function for A. So now let's look at part B, and I'm going to use the same graph. So I'm just going to get rid of the function from part A and we'll start over. So let's look at B. So we have two equations. Y, or f of x, is equal to 1/2 x squared. but only if x is less than 1. So let's do what we did above. Let's make a table of values. I know 1 is not part of this domain, right? Because x has to be strictly less than 1. But let's use it because that's going to be where I'm going to put an open circle. So, because the graph is not going to go past that point. So look, let's use 1 for x. Plug it into my equation. So 1/2 times 1 squared. 1 squared is 1. 1 times a half is a half. So we have the point 1 comma a half, but that's going to be an open circle. Now let's pick some other values that are less than 1, right? How about 0? If I plug in 0, I'm going to have 1/2 times 0 squared, which is 0. Pick another number that's less than 1. How about -1? -1 squared is 1, and 1 times a half is a half. Let's pick another value that's less than 1. How about -2? Plug in -2 into my equation, so 1/2 times -2 squared. Well, -2 squared is 4. 4 times a half is 2. And this 1/2 x squared is a quadratic, right? Because there's an x squared term. So let's plot these points and see what it looks like. So we have the point 1 comma a half, and let's put that one in green because we're going to have an open circle on that, right? So I'm going over 1, and then let's go down a half. So it's going to be like right here. So there's my open circle. I'm sorry, up a half. I'm not paying attention. Sorry about that. So we're going over 1, and then a half is going to be halfway between 0 and 1, right? Then we have the point 0, 0. Then I have the point -1 a half. And then I have the point -2, 2. And so on and so forth. We could do one more point, like if we did -3, so if we were to add -3 here and plug it into 1/2 times -3 squared, -3 squared is 9. 1/2 of 9 is 4.5. So we would have the point -3 and then about 4.5. So now we could really see this parabola, right? But it stops right where that green open circle is. We can't go past that because this is only defined for values of x that are strictly less than 1. So we see kind of like a half of a parabola here. Now let's graph the other equation. So now let's graph f of x or y equals 2x minus 1. And that's only for values of x that are greater than or equal to 1. So let's make a table of values and pick values of x that are greater than or equal to 1. So let's use 1. So if I plug 1 into my equation, I'm going to get 2 times 1 minus 1. 2 times 1 is 2. 2 minus 1 is 1. So I have the point 1, 1. Pick another value greater than or equal to 1. What about 2? 2 times 2 is 4. 4 minus 1 is 3. Let's use 3 because 3 is bigger than or equal to 1. 2 times 3 is 6. 6 minus 1 is 5. And this is a linear function. So 3 points are always good enough to make a line. So I have the point 1, 1. We have the point 2, 3. And then I have the point 3, 5. So my line is going to look like this. So this is what my piecewise function would look like in this case. So I think the best strategy to graph these piecewise functions is look at each equation one at a time, make a table of values, but make sure you're picking values of x that are part of that particular domain that's assigned to that equation. So the last thing that we're going to cover is the difference quotient of a function. The difference quotient is a quotient, right? A quotient is just a fraction. So look, we have a big fraction here. And in the numerator, we're taking the difference of something, hence the difference quotient. Now, what are we taking the difference of? So we're taking the value of our function at x plus h. So we're evaluating our function at x plus h. And then we're subtracting f of x, which is the function itself. And we're dividing by h, where h is not allowed to be equal to 0 because we can't divide by 0, right? Now, you're not expected to know what this means in this class. You're going to learn more about the meaning behind difference quotient once you get to calculus. But it's used when calculating rate of change. And I'll tie that in after we do example A. So what do we want to do in example 5, part A? So for example 5, it says evaluate and simplify the difference quotient for the following functions. So let's look at example A. So we want to find and simplify the difference quotient. So if my function in A is f of x equals 3x plus 7, we want to find and evaluate f of x plus h minus f of x divided by h. So first we have to find f of x plus h. Now, f of x plus h is just evaluating the function at x plus h. So wherever we see an x, we're going to replace it with x plus h. So look, we're going to take f of x, which is 3x plus 7, but we're going to input x plus h first. So we're going to have 3 times x, but we're replacing it with x plus h plus 7. So this is f of x plus h right here. 3 times x plus h plus 7. But then we subtract, so we need to subtract f of x. And f of x is just 3x plus 7. This is just the function itself. And then we divide by h. So this represents the difference quotient for f of x equal to 3x plus 7. But now we could simplify it. So look, we could distribute in the numerator. So we're going to have 3x plus h plus 7, right? So all I did was distribute the 3. Now I could distribute the negative. So I'm going to have minus 3x minus 7 and then divided by h. And now you see, we could go to combine like terms, but look what happens when we go to combine like terms. A 3x and a negative 3x sum to 0. A 7 and a negative 7 sum to 0. And then all we have is h over h. And that simplifies to 1. Hold up, I knew something was wrong. I'm looking at this and I'm like, I know I'm not supposed to get 1. The answer is supposed to be 3, and I'll explain why that is in a minute. I hope some of you caught my mistake. So let's back up for a minute. I hate to confuse you. Here, let's back up. But when I distributed, I missed the 3h. So look, 3 times x, let's go back to this part where I'm going to distribute. So 3 times x is 3x. 3 times h is 3h. Then plus 7. Now minus 3x and then minus 7. This is much better. So now let's go through and combine like terms. So we have a 3x and a negative 3x, they add to 0. We have a 7 and a negative 7, they add to 0. And we're left with 3h over h. And then, of course, the h is reduced to 1, right? And my answer is 3. So my difference quotient for that function, 3x plus 7, is equal to 3. And what's significant about this, remember before I said it has to do with rate of change? Well, this is a linear function, and the slope of this line, right, because this is in the form y equals mx plus b, the slope m is 3, and slope represents average rate of change. And look, my answer to this was 3. So like if we look at the next one, b, I have another linear function, 6x plus 1, right? Y equals mx plus b, where now 6 is the slope. And that's the rate of change of this function. So I'm thinking, okay, when I find the difference quotient, it should be equal to 6 if that's what this represents. So let's do this. So we're going to do the same thing that we did before. So we have f of x plus h minus f of x divided by h. So let's find f of x plus h. So let's evaluate the function at x plus h. So wherever I see an x, I'm going to replace it with x plus h. So we're going to have 6 times x plus h plus 1. That's f of x plus h. Now let's subtract f of x, which is 6x plus 1, and divide by h. Now we can distribute, and I promise I'm going to do it correctly this time. So we have 6x plus 6h plus 1. Now let's distribute the negative, so minus 6x minus 1 over h. And let's combine like terms. I have a 6x and a negative 6x, which sum to 0. I have a 1 and a negative 1. They also sum to 0. And I have 6h divided by h. H over h is 1. And my difference quotient simplifies to 6, which also represents, the average rate of change of that function. This is always going to be the case when we use the difference quotient on a linear function. But look at the next example, C. This is a quadratic. It's not a linear function. So it's going to be a little bit more involved. And you'll really understand more when you get to calculus in terms of, average rate of change for something like this, like a quadratic. But let's find and simplify the difference quotient for this one. So we're going to take f of x plus h, subtract f of x, divide by h. Just move this over a little bit. Okay, so f of x plus h, so remember, wherever we see an x, we're going to replace it with x plus h. So instead of x squared, I'm going to have x plus h squared, then minus 4 times x, but we're replacing it with x plus h, and then plus 3. So this here represents f of x plus h. Now we have to subtract f of x, which is the x squared minus 4x plus 3. And then we divide by h. So now, because it's not a linear function, now we have a quadratic, which involves an x squared term. It's a little bit more work in terms of the algebra. So x plus h squared is x plus h times x plus h. We could just do this now, distribute the negative 4 in the next step. So we have minus 4x and then minus 4h plus 3. And then we could distribute the negative, right? So we're going to get minus x squared plus 4x minus 3 over h. So look up here. I'm going to do x plus h times x plus h. We're just using distributive property, right? FOIL. So this is going to be x squared plus xh plus another xh and then plus h squared. And we could combine the two xh's, right? So we're going to get x squared plus 2xh plus h squared. So anytime you have to multiply x plus h times x plus h, it's always going to be equal to x squared plus 2xh plus h squared. Now we have minus 4x minus 4h plus 3 minus x squared plus 4x minus 3. And this whole thing is over h. So now let's go through and combine like terms. So I say I have a positive x squared and negative x squared. They sum to 0. I have a negative 4x and a positive 4x. That sums to 0. I have a positive 3 and negative 3. That also sums to 0. So all I have left in the numerator is 2xh plus h squared minus 4h over h, right? So I just have those three terms left in the numerator. And now everybody has an h in common, right? Everybody is divisible by 1h. So my simplified answer is going to be 2x plus h minus 4. And that wraps up this section. In the next lecture, we're going to begin 2.3, and we're going to talk about definition of slope with the linear functions.